Okay, let me start. So thank you for joining me today. I will go through the second option or the second case for your design. But first of all, I would like to remind you with the first case. The first case, we are given everything about the cross section, the width, the depth of your steel reinforcement, and how much steel reinforcement do you have. So the cross section is given, or you can assume the cross section. And then I'm looking to figure out how much design moment strength of this cross section, phi mn. Keep in your mind, we have stress distribution. This stress distribution, we have neutral axis. This one at a depth actually equal C, but we have a stress block with a depth equivalent stress block with a depth A. This stress block can be converted to a compressive or a compression force, capital C. This capital C equal 0.85 F prime C A B. And we have tension force at the bottom in the steel reinforcement. This tension force equal area steel F yield. For equilibrium, the two forces are equal. So I can figure out the missing term, which is A. After you get A, keep in your mind that the distance between the two forces equal depth minus A divided 2. So your nominal moment of resistance will be one of them, the T or the C. It's up to you. T time depth minus A divided 2. So the T equal area steel F yield, and your distance depth minus A divided 2. Once you get your Mn, I will multiply this N by a term called phi. Once you multiply your Mn by phi, this term will be called design moment strength. And this moment or this design moment strength for this cross section must be greater than or equal the moment which is coming from structural analysis, M ultimate. Later, we will cover how to figure out this value, M ultimate. Keep in your mind to figure out the value of phi, which is called strength reduction factor. This strength reduction factor phi can be figured out from this table. We have three cases. Based on how much strain in the steel rebar, we must draw the strain distribution at this neutral axis. We have 0. At the top, we have compression. At the bottom, we have tension. At the top, we have strain in concrete, which equal 0.003 according to ACI. At the bottom, we have a value called epsilon T. I don't know how much is this. Then I will do triangle similarity between the top triangle and the bottom one. Keep in your mind, this is C, the depth of your neutral axis, which has a relationship with A equal beta times C. I know A from the first step. I can figure out the value of beta based on the value of F prime C. Then I can figure out this distance C. And the remaining distance here for the other triangle will be the depth minus C. Then I can set up the triangle similarity to figure out the value of epsilon T. Or you can use this expression if you want. That's fine. Once you get the value of epsilon T, keep in your mind we have a value called epsilon yield, yielding strain. This yielding strain equals the yielding stress divided by the Young's modulus of steel. Yielding stress will be given in the problem, something like 50, 60, 65. E steel equal 30,000 KSI. If you divide this number by this number, you can get the value of epsilon yield. I will do a comparison. between epsilon t from this triangle similarity and the epsilon yield from this expression to find yourself in this case or this case or this case. Does that make sense? And we covered solved examples, one solved example last meeting. I will start with the second case, case number 2. The case number 2 is the cross section of your concrete is given, only the cross section. What is the width? What is the depth? You can assume them, they will be given for you, that's fine. But the area steel is unknown. I don't know what is the value of epsilon steel. It's unknown. However, the value of the applied moment from structural analysis is already known. So I would like to convert this moment, which is coming from structural analysis, to how much steel reinforcement I need. So go ahead, cross-section is given, dimensions of the cross-section, the moment coming from structural analysis M ultimate is given, and we are looking for how much steel reinforcement. How much steel reinforcement we are looking for. We have few steps. The first step, I need to figure out what is the value of this expression. How much value of this expression? M ultimate divided by phi b d square. So I need to figure out what is the value of M ultimate divided by phi b depth square. Keep in your mind, this moment M ultimate must be pound per inch. The numerator must be pound time inch. And this value of phi will be taken 0.9. This b will be an inch. This depth will be an inch. From this value, from this expression, I can get a value. Using this value, I will open a table. I will show you this table just a moment. Once you open a table, I can find the value of rho. From this table, I will find the value of rho. This value of rho is called reinforcement ratio. This rho is called reinforcement ratio. One more time. One more time. I will use this expression, M ultimate divided by phi b d square, to find a value. This value, I will use it through a table. This table will give me the value of rho, which is called reinforcement ratio. This rho must be, I need to check it. This rho must be greater than or equal rho minimum and smaller than or equal rho maximum. I need to check, make sure the value of rho from this table based on this value is greater than or equal a rho minimum, the minimum reinforcement, and the smaller than or equal the maximum reinforcement. Your check is okay, then I can say this value of rho equal the required area steel divided by B time depth of the cross section. So far, I know what is the value of rho. I know what is the width of your cross section, what is the depth of steel reinforcement. From this expression, I can figure out the value of area steel. Once you get your value of area steel, I am done. The basic here, we are looking how much steel reinforcement needed to support this M ultimate. I am done. Let's do an example and see how these tables will looks like. By the way, I uploaded these tables on D2L lecture notes. You will find the PDF file called tables. In these tables, you are going to use this file many times during your homework, during your exam, during your life. This tables, this file including very variety number of tables. One of them, for example, at the first page is the number of bars. Number 3, number 4, number 5, number 6, number 7, and so on. And what is the cross-section area for each rebar? This is a good point. This is a good table, and we have to pay attention to it. Also, we have a table here. If you would like to use it, that's fine. Based on the value of F prime C, this table can tell you what is the E concrete. If you remember last week, we have a value called the modular ratio, which equal E steel divided by E concrete. And we covered before E concrete equal 57,000 square root for F prime C. If you don't like to use this expression, go ahead and use this table. Based on the value of F prime C, I can tell you what is the Young's modulus of concrete. That's fine. What else? We have many things in this table. In these tables, we will use them one by one later. But let me go down more. Here you go. Starting from table A7. If you remember, I told you we will check the value of rho between rho minimum and rho maximum using table A7. Table A7. In this table A7, we have values for F yield. This is based on the steel reinforcement. I will tell you which grade of steel reinforcement we are using. And this one based on the value of F prime C. What is the compressive strength of concrete? 3,000, 4,000, 5,000, 6,000, and so on. Based on the F prime C and the type of steel, I can tell you what is the value of rho minimum. And I can tell you what is the value of rho maximum. Your rho maximum will be this one. This is the rho minimum, and this is the rho maximum. This one. Rho at epsilon t equal 0.005. We can use this one as the rho maximum. That makes sense? I do prefer to use this value as your rho maximum. So we have rho minimum. I can put it here. We have rho maximum. I can put it here. And I can check my rho value. So for example, if the problem saying we have F prime C equal 4,000 PSI, and we have steel reinforcement with F yield equal 50,000 PSI. Anybody in this room can tell me what is the value of rho minimum? What is the value of rho maximum? Very easy. Very easy. First of all, the value of F prime C 4,000. This is the one. The value of F yield, the type of steel is 50. So we have 50,000. Based on this column and this column, I can tell you the value of rho minimum will be 0.004. And the value of rho maximum will be 0.0 217. That makes sense? It's very easy. Based on the value of the F yield and the value of F prime C, I can tell you the rho at epsilon equal 0.005. We would like to use this value to make sure the phi equal 0.9. And we have F yield. And the rho minimum is given 0.004. So we need to make sure your value of rho is greater than or equal rho minimum and smaller than or equal rho max. This is the table A8. So we will use table A8 to figure out the value of rho. So I will figure out what is the value of M ultimate divided by phi BD square. Then I can tell you what will be the value of your rho. Does that make sense? Let's do an example and see how to figure out the amount of steel reinforcement. I think we have two examples, example number 2 and example number 3. Let's start with example number 2. We are given this cross-section where B equal 14 inch and your depth equal 21 inch. Keep in your mind your depth is measured to the steel reinforcement only from the top to the steel reinforcement. Looks good. And the applied ultimate moment means M ultimate. MU means ultimate moment. We have this moment M ultimate equal 100 kib foot. This M ultimate equal 100 kib foot. And we are given the steel reinforcement if yield equal 60,000. And the value of F prime C compressive strength of concrete, F prime C equal 3,000 PSI. If you would like, before starting to figure out how much area steel we need, from these two values, F prime C and F yield, I can tell you what is the value of rho minimum, what is the value of rho maximum. Using the table A7. If we go back to this one, with F prime C equal 3,000 and the F yield equal 60,000, I can tell you the value of rho minimum, this one and this one. So we are looking for these values. That makes sense? And the value of rho minimum 0.0033. And the value of rho maximum will be 0.0136. This is the first step before starting. Then I will figure out the value of M ultimate divided by phi BD square. Your moment ultimate is given. How much? 100. But this moment must be in pound and inch. So I need to convert this unit to pound and inch. So I need to multiply it by 12,000. Do you remember? If you have this value in pound inch, I will divide it by 12,000 to be kib foot. Right now we have kib foot. Go ahead and multiply it by 12,000 to be pound inch. Divided by phi 0.9. B, the width of your cross section is 14. Your depth is given 21 square. Using my calculator, 100 times 12,000 divided by 0.9 times 14 times 21 square. I got 215.9. Then I'm gonna use my table to figure out the value of rho, how much, based on this value of M ultimate divided by phi BD square. So I will open the next table, but unfortunately, the next table for F prime C equal 3,000 and F yield equal 40,000. We have 3,000, yes, for concrete, but 60,000 for yield. F yield, so this table will not work. Keep going. We will have one more. Actually, many more. This one for 40,000 and, I'm sorry, 40,000 and 4,000. No, not this one. Keep going. Maybe this one, 50,000. No. Keep going. This one, 50,000. No. So go down more. One more. Yes, here you go. We have here table A12. With F yield equal 60,000 and F prime C equal 3,000. I think our problem is going to use this table, 3,000 and 60,000. Does that make sense? So table A12. Table A12. So I will not say a specific table number, but based on the value of F yield and F prime C. Keep in your mind the value of M ultimate divided phi BD square 215.9. So I will look for 215.9. 215.9. If you look here, we have 200, we have 215, 212, 217, 223, 206. Looks like we don't have 215. So the closest number to 215.9 will be 217.8. The value of phi, I'm sorry, M ultimate divided by phi BD square equal 215 point something, 0.9. The nearest value in this table is 217.8. That's fine. Go up, don't go down. So we have 212. No, I'm gonna use 217.8. The corresponding value for this value is rho equal 0.0038. So first of all, which table I'm gonna use? The table with F yield equal 60,000 and F prime C equal 3,000 based on the given information. Next step, based on the value of M ultimate divided by phi BD square, I put my hand on the nearest value, the nearest upper value. Then I can figure out the corresponding value of rho. Rho equal 0.0038. Is it 1 O or 2 O? One more O, 38. Before going forward, I need to check that your rho from the table, this table, is greater than or equal rho minimum and smaller than or equal rho maximum. Is it correct or not? If it's not, we need to think more. Your value of rho is 0.0038. Your rho minimum at the beginning 0.0033. The rho maximum 0.0136. I believe that my rho is greater than the rho minimum and smaller than the rho maximum. It's okay. Move forward. Move forward. And keep in your mind, this condition must be satisfied to make sure we are moving good and our design is correct. Your rho value equal 0.0038. This rho value, which is 0.0038, equal the value of area steel divided by B time depth. Your value of B equal 14 and the value of depth equal 21. So this one is 14, this one is 21. The only unknown in this expression is your required area steel The required area steel will be 0.0038 times 14 times 21. I got 1.12 inches square. So the cross section will need area steel equal 1.12 inches square. Anybody has any question so far?
No, sir.
I would like to convert this area steel to how many rebars? So I will put 3 rebars, 4 rebars, 6 rebars, 10 rebars. I cannot tell you until you tell me if you selecting number 3 rebars, or selecting number 4, or selecting number 5. Let's try. For number 3 rebar, I will go up here. For number 3, the area for this rebar is 0.11. So if you divide 1.12, this is the required area steel, by 0.11, this is the area for one rebar number 3. If you divide this number by 0.11, I'm sorry, this area steel by 0.11, so looks like I will need 11 rebars number 3. If you try number 4, what is the area for rebar number 4? It's 0.2. So if you divide 1.12, the required area steel, by 0.2, looks like I will need 6 rebars number 4. Let's try number 5. If you use the number 5, the area is 0.31. This is the area for one rebar. So if you divided the total area of steel by the area of one rebar number 5, I will need 4 rebars number 5. We have these options, and it's up to you as a designer. You can say, okay, guys, I will use 4 rebars number 5. These rebars will give you an area steel equal 1.12 or greater. And these rebars will satisfy will support the applied moment 100 kb foot. One other, Thomas will say, no, I don't like number 5 rebar. I will use the second option. I will put 6 rebars number 4. That's correct, because 6 rebars number 4 will give you the required area steel and will satisfy the applied moment. Another one, Andrew, for example, will say, I don't like number 5 or number 4. I will use number 3, so I will put 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But I do prefer the number here because we will have 2 rows to be even number. But I don't like this option because more numbers of rebars is not good. For pouring concrete, this is just for construction, but for design, that's correct. But we have another factor, which is the construction, and we are worrying about pouring concrete and nesting and segregation, all of this stuff. We don't like many numbers of rebars. So this option is good. This option is good. You have to tell me one option of these, and it's up to you as a designer. Let's do one more example. I have another example here. Wow, the problem did not give anything, just read. We have reinforced concrete, simply supported beam with an effective span 20 feet. So we need to translate. We have a beam, simply support means between 2 support only. The span of this beam, the total span equal 20 feet. And we are given the cross section of this beam with overall depth 24. This is the total height. Overall means, this expression means the total height equal 24 inch. And we are given effective depth. So this depth to the steel reinforcement is 20. And we are given the width of the cross section is 12. So far, so good. We need to translate our problem to sketch. We are going to use steel rebars grade 60. Steel rebar grade 60 means if yield equal 60,000 psi. If you open your table, we have here in this table, not this one, yes, this one. For steel reinforcement grade 60, this is the one of grade 60, your F yield equals 60,000 psi. That makes sense? And we are given concrete compressive strength F prime C equal 4,000 psi. We need to figure out how much steel reinforcement determines the area of reinforcement, area steel. This area steel is unknown. To support or to carry dead load equal 0.75, we are given here a uniform distributed load 0.75 kb per foot. This is your dead load. And we have 1.1 kb per foot. This is your life load. We are given an information here, which is very important. We have dead load 0.75, but this dead load does not include the on weight of the beam. This is a good point. On weight is not included in this number, 0.75. And we have life load equal 1.1. So I need to start first with the structure analysis step. To figure out the on weight of the beam, you need to multiply the width by the thickness by gamma concrete. I believe you learned this during the maybe building construction course. This is your cross section of the beam. So I will multiply this width by this thickness by gamma concrete to figure out the weight as unit weight, unit length weight. So your width is given in this problem 12 inch. Your total thickness of the cross section is given 24 inch. Your gamma concrete, you must be aware of this value, 150. Gamma of concrete is 150 pound for each cubic feet. 150. You have to keep this number in your mind. I cannot multiply 12 by 24 by 150 because the units are not matching. So I need to convert this number to feet. I need to convert this number to feet. Then I can multiply it to 150. So it will be 300 pound per foot. So for every foot, 1 feet of this beam, the weight of this length equal 300 pounds or equal 0.3 kib per foot. I divided it by 1000. Keep in your mind, the dead load in this problem is given by 0.75, which is not including the on weight. So the dead load total will be 0.75, which does not include the on weight of the beam. I need to add 0.3, which is the on weight of the beam, because your own weight is considered dead load also. So 0.75 plus 0.3, the value will be 105 kib per foot. And your life load will still the same, no change in this life load, 1.1 kib per foot. Keep in your mind, we have combination according to ACI, ASCE, that was covered in the first week. You will, if you go back, you will have 1.2 dead load plus 1.6 life load. One of the combinations that I can combine dead and life is this expression. 1.2 dead load plus 1.6 life load. We don't have wind, we don't have roof life load, we don't have earthquake, we don't have snow, we have only dead load and the life load. So if you search in these combinations, you will see this equation. So the W ultimate, the total uniform load, ultimate uniform load will be 1.2 times dead, 105, plus 1.6 times life, 1.1. This is the total combined load, 1.2 times dead, plus 1.6 times life. It will be 0.02 kib per foot. So guys, because we have dead load and we have life load, I need to combine both of them. So I need to look to the load combinations according to ASCE. In the first module, you will find this expression because we have dead and life only. So I will put the value of dead and the value of life besides 1.2 and 1.6 to get the final value of the load. So right now, I have a beam with effective span 20 feet based on the given information. And this beam under the effect of uniform distributed load after your combinations and the combined dead and life equal 3.02 kib per foot. So I can tell you based on the structure analysis, the bending moment diagram will be like parabola. The highest value of this parabola will be WL square divide 8. So W is 3.02, L square 20 square divided by 8. This value will be 151 kib foot. This is the value of M ultimate. Oh my goodness. In the previous example, M ultimate is given. So I started from here. But in this example, M ultimate is not given. So I looked to M ultimate. based on the structure analysis. Structure analysis saying what is the value of the own weight based on this expression. Then I need to add this own weight to the remaining dead load, which is given. This part of the dead load is given. This is the dead load coming from the own weight. How did you know this? If you read here, this value of dead load does not include own weight. So this is the reason why I need to calculate how much own weight and need to add this value to the given dead load. This is the total dead load. And the life load is given. I need to add this one plus this one. So I need to do combination. According to ACI 7, we have this equation for combination between dead and life. So I put the value of dead and put the value of life to find the final total load on the beam, 3.02 kb/foot. So your beam under the effect of this uniform distributed load, according to structural analysis, the bending moment diagram will be a parabola. The highest value of this parabola is WL squared divided 8. So W equals 3.02, L squared 20 squared divided 8. The final value is 151 kb/foot. This is your M ultimate coming from structural analysis. Does that make sense? Then I will start my design. M ultimate is given. Right now it's given 151 kb/foot. If yield is given, if prime C is given, if yield is given 60,000, 4,000. PSI. Let's go. I will start with these two information to figure out what is the raw minimum, what is the raw maximum, to make sure your design is good. So I will open the table with F yield 60,000, F prime C 4,000. This is the table for 4,000. This is a column for 4,000, F prime C. This is the table for 60,000. So I need to use these values. Does that make sense? So the raw minimum will be 0.0033. The value of raw maximum will be 0.0181. Then I will start to figure out the value of M ultimate divided by phi BD square. M ultimate after structural analysis is 151, but this one in kb/foot, I will multiply it by 12,000 to be pound inch. Divided by phi, I'm assuming 8.9. Your B of the cross section is 12. Your depth is 20 times 20 inch square. So I can find my value. $419.4. Then I will open my table. I'm gonna use this value, but keep in your mind, I'm gonna use the table for 60,000 and 4,000. So I need to go down, down, down. It's too much. Yeah. This one 60,000, 4,000. We are good here. This is the table. 60,000, 4,000. 60,000, 4,000. We are good. This one and this one. And your value is 419. 419. So 400, 400, we have 400. Yes, we have 414, we have 420. Your value M ultimate divided by phi BD square equal 419.4. So I'm gonna use 420. This is the nearest upper value. The corresponding value for rho is 0.0075 based on this table. 0.0075. 0.0075. I need to make sure your rho is greater than or equal rho minimum and smaller than or equal rho maximum. Go ahead and put your numbers. 0.0075. This one was 0.0033. This one was 0.0181. I think, yes, my rho from the table is greater than rho minimum and smaller than rho maximum. It's okay. So this rho equal actually area steel divided by B depth. So 0.0075 equal the required area steel divided by B12. Your depth in 20 inch. So I can figure out the required area steel. It will be 1.8 inches square. How many steel rebars? Please, I need to convert this area steel to how many numbers of rebar. If you are going to use number 4, how many? If you are going to use number 5, how many? If you are going to use number 6, how many? For number 4, your area steel 1.8 divided by 0.2. This is the area of number 4. So 1.2 divided by 0.4. I will need 5 rebars. For number 5, I will divide 1.8, the required area steel, by 0.31. This is the area of number 5. I will need 6. No, wait. This one, I will need 9 rebars. I'm sorry. For number 5, I cannot remember number 5. What was the area steel? Number 5 is 0.31, yes. 0.31, so 1.8 divided by 0.31. I got here 6 rebars. For number 6, if you are using number 6, for example, it will be 0.44. So 1.8 divided by 0.44. Let's try this one. I will need 5 rebars. And if you would like to try more, go ahead. And it's up to you. It's up to you as a designer. As a designer, I see that I'm going to use this one. 5 rebars, 1, 2, 3, 4, 5. Number 6. This will be good. 5, number 6. Or you can use 6, number 5. That's fine. But I don't recommend the mini rebars number. I don't like too much rebars. So the final conclusion for this beam, I will provide at the bottom of this cross section, I will provide 5 rebars, number 6. This number of rebars will be enough to support the applied load dead and life and the own weight of the beam as well. So sometimes if the M ultimate is given, you need to start your design directly. Sometimes in this problem, M ultimate is not given, so I need to start with the structure analysis part. First, structure analysis part means what is the value of dead load? What is the value of live load? You are lucky because the value of dead load in this problem is not enough, is not total. We need to add the own weight. So I figured out what is the own weight of the beam. Added them together to find the total dead load. And the total live load is given. Then I do combination. Then I put my final combined dead and live load on the beam to draw your bending moment diagram. The highest value in this diagram is called your M ultimate. Then after this step, I need to start my design. We have different steps. Your design based on your M ultimate, F yield, F prime C. I can check the rho minimum, rho maximum. I can find out the value of this expression, open my table to find out the row, make sure your row is greater than row minimum and smaller than row maximum. This row equal area still divided by BD. Everything is known. I can figure out the required area still. Then I can convert this area still to how many rebars. You need to assume if you have number 4, if you have number 5, if you have number 6, and then your final conclusion is up to you.